So Ariela, you can unmute and give us an opening prayer. Okay, okay, Bruce, proceed. I think Ariela is not ready.
Let us may your name be glorified. Achieve success in our academics. When everything is done, we shall stay glorifying your name. So, in the name of the Father, the Son, and the Holy Spirit, I pray. Amen.
Amen. Hey, you are done. Okay. So, we are going to introduce this topic. So, for those who covered it from school, yeah, that is very okay if you covered it from school, but we are going to try our level best. Yeah, we are going to try our level best to introduce it. So, for those who never covered it from school, yeah, still stay tuned and stay alert. We're going to cover it. So, again, let me share the screen. Thanks for the prayer, Bruce. I think this is where we are. So that is the screen, yeah? Okay, I don't think we need this. We shall leave it. I also don't think we need this. So let me see those people in the chat, yeah? I want to get the tone of the topic first before I even introduce. If you covered, you say covered. If you've not covered, you say not covered. If you covered part, you say covered part. I want to be driven by the tone that I'm going to get from the chat at least, so that I don't leave anyone behind, so that I don't waste anyone's time, such things. I want to see it in the chat. Then my chat secretary will give me a general report that the most people never covered. So my chat secretary should be alert. Okay, I think that's enough time for people to comment about the topic. So has been following all the texts. Raise up your hand and tell me what most people have said in the chat. Fully covered, not covered, halfway covered. Okay, please, the person who read me something, stop writing in our screen. Hey, sorry about that. I've been actually speaking. So I was saying, I think most people have not covered the topic, so we are going to introduce it. So one thing I urge you members, you're using smartphones, and all smartphones take screenshots. Even when you're using a laptop, you can print screen. You understand? And then you later sit down after the class and organize your work. Then you later use that work for revision. So I want you to be very sober. Take screenshots even when I don't ask you. Yes, I want you to be that organized because you realize it is only recordings that I share. I don't share my notes after. Yes, and I don't want you to ask me for my book after this lesson. I was going to use something else, but for today, I've decided to use one of my books. I've decided to use one of my books, and that is the book. Yes, I have my own book. It has all topics in line with what you people are supposed to cover. But of course, I'm still working on it. They are not yet ready. That's why no one has them except me. But with time when they are, I'll literally release them all. So we are going to introduce the topic. As usual, in the old curriculum, this was chapter 4, topic 4, but in the new curriculum, it is chapter 5 or topic 5, and it is a term 2 topic. That's why most of you guys have covered it, but that won't stop us from revising it. Okay, so we shall come here. So this is my student-friendly syllabus book. You cannot find it anywhere. You cannot find it anywhere. Unless that one person I trusted leaks the copies. But I'm still organizing them more so that you people receive something that is so good. So before you go back to school, make sure you have this student-friendly syllabus book. You go with it. It will surely be of use. So don't leave it behind when the term starts. I beg. Okay. So it's divided into 3 subtopics. So the first subtopic is called enthalpy changes and energy profiles. Yes, enthalpy changes and energy profiles. And then this is what they expect us to learn, and I assure you we are going to look at it. All of those ones are getting done today. So yeah, I would say getting done today. So the whole of that first subtopic, remember there are 3 subtopics. Today, so when we are finishing it, 3 subtopics, 3 lessons, and thermochemistry will be done. Then subtopic 2 concentrates on the types of enthalpy changes and Hess's law. So concerning this portion of the types of enthalpy changes, I want to teach all of them today. Yes, and you know what I mean when I say that today. Why do I want to teach them today still? Because when you look at subtopic 1, it has enthalpy changes. So what does that imply? That I'm going to teach enthalpy changes, their types, and energy profiles. You understand? Now, the other thing that they want is Hess's law. Under subtopic 2, Hess's law. Hess's law is to do with calculation. So in this lesson, I'm not going to do any calculation. I'm not going to do any calculations. So calculations shall be for lesson 2. You understand? Yeah, that's when we shall work on this. Eh? So this first one is for today. But the moment Hess's law comes in, anything to do with calculating thermochemical equations and enthalpy data, that will be next lesson of thermochemistry. That will be the next lesson. Okay. When I proceed down, it is 5.3. This will be a special lesson on its own. Yeah, this will be a special lesson. Special lesson. That one. So we shall also read through all this next time when that special lesson reaches. It will be one single lesson and we shall handle all those things. What lattice energy means, what hydration energy means, what enthalpy of solution means, or the solvation energy and other things. That is a special lesson alone. Then the next lesson, this special lesson shall be lesson 3. But unfortunately, all these ones shall be premium lessons. Oh, those ones will be premium lessons. So even this next lesson concerning Hess's law and other sorts of calculations. So this is the lesson that will have other calculations. That lesson we shall just log on to calculate non-stop until the lesson is done. And this will be lesson 2 of thermochemistry. It will be lesson 2. Yes, calculations. But for today, lesson 1, we are going to be just introducing the topic generally. We look at enthalpy changes, their types and what? And energy profiles. And we shall be done. Hope that is okay. Hope the wise people are taking screenshots as I said. You target me, you take one. You target me, you get one. You target me, you get one. So that you go with the plan. Okay. So I can now come and write lesson targets. So lesson targets. Enthalpy changes. Energy profiles, and then types of energy changes. But of course, you all know all these things come after first things first introducing the topic. So one, we should introduce the topic. So introduction. After the introduction has been successful, can now come handle enthalpy changes, shall handle energy profiles, shall handle types of what? Enthalpy changes. So introduction, we are going to read it together, eh? And that's how we are going to be in position to save time. So we are going to read the introduction together. I want you to be very sober, to take screenshots when you alert. Do you mind sharing your books? I can't. Yeah, free lessons are stopping today. Yeah, because at night you're having biology. So this is the last free lesson. So these are our notes written by me, but they are not yet ready. But they'll be ready, especially when UNEB releases the form of assessment, so that I can put some sample papers. So I want you to learn something, that the topic thermochemistry has two words. So intro. So thermochemistry, of course, you people know what chemistry is. This is something you defined in senior one. You know what chemistry is. Now here, thermo means energy, but strictly which form of energy? Heat. And we are going to see how these things are studied. Chemistry, you know what it means. Study of changes, which may be energy changes. So for thermochemistry, it is strictly about what? Heat changes. Yeah. So we're going to see whatever we are going to be looking at in this topic is going to be about heat given out, heat absorbed, heat evolved. So don't be confused when those words dominate the topic. It's simply because it's what we are handling. Thermochemistry is a study of chemistry alone, study of changes of energy. Which form of energy here in particular? Heat energy. Of course, you know thermometers deal with heat. So you know, thermometers deal with heat or temperatures. So heat, just like that. Okay. Now they are saying thermochemistry is the study, so we read together, is the study. So a wise person has already taken the screenshot. Is the study of energy changes that accompany chemical reactions. So it is simple that as chemical reactions are taking place, what do we have? We are having energy changes taking place. And you like it or not, these energy changes they are talking of here are strictly heat changes. The form of energy here is heat energy. So they are heat changes. They are saying that the topic is also called chemical energetics, and you're going to see why. Or the topic can be called chemical thermodynamics. All those are names of the topic. So I don't want someone to ask you, did you do chemical energetics? Then you'll be like, no. So it is the same name. So the mere fact that it is called chemical energetics, we need to study about chemical energy. And before I proceed, I want to tell you something about chemical energy. Why chemical energy? Because we are dealing with a chemical reaction. If it is called a chemical reaction, that means the people that are taking place, or the species, or whatever is taking place in the reaction is a chemical reactant. And the product we expect is a chemical product. So because of that word chemical, chemical, chemical everywhere, we assume that whatever is reacting possesses chemical energy. And you people know what they call the laws of conservation of energy from physics O level and primary. And what do they say? They say that you don't just lose energy anyhowly. But in most cases, when you lose energy, it is converted into some other form. So the energy has not been actually lost. It has been conserved. You remember those things? It's like sounding a bell. You know that some form of energy is what turns into sound energy. You get? You remember those things even in motors. When something is at rest, it is having potential energy. When it starts moving, it's having kinetic. So the potential energy it had while resting has not been lost, but it has been transformed into kinetic when motion actually started. You understand? So the same thing happens in reactions, that the chemical reactants we have possess chemical energy. And when a reaction takes place, that energy is not lost. That energy is converted into some other forms of energy like heat. Basically, in this topic, someone may be like, what really makes that heat to come out? Do you just command the heat to come, like the heat come out? Heat get absorbed, heat get evolved? Not really. Something must be done to that reactant for you to notice either a change, either an increase in heat or a decrease in heat, or I will say, so that you notice either evolution of heat, or what we call giving out of heat, or what we call releasing heat, versus absorbing heat. For you to notice such changes, you must do something to this chemical reactant. And what are those things you do? You can burn it in oxygen, what they call combustion. Those who attended chemical equations with me last holiday, you know what combustion is. If you don't combust it, add it to water, or add water to it. If you don't add water to it, add an acid. If you don't add an acid, get another chemical reactant and make them react by force. You understand? Why am I bringing all that? That you may not notice any change in the heat energy of the reaction unless you trigger a certain reaction. So for you to notice any energy change, a reaction must take place. Which reaction? May be burning it in oxygen combustion, adding an acid, adding water, getting another reactant, and forcing them to react. That's when you can notice and be like, oh, heat has been released. Oh, heat has been absorbed. You know the machines that measure these energy changes. We are going to also see some down. Okay. So let's read about chemical energy together. I told you just be alert, take screenshots, write your own notes. Okay. Chemical energy. So I'm saying that energy is the capacity to do work. You know that? There are many forms of energy, among which chemical energy is one. We have sound, we have heat, we have electrical, we have a lot of things. What are they saying? They are saying that chemical substances also have the capacity to do work, which work is to react. And the mere fact they have the capacity to do work which is reacting, they have energy. And which form of energy? Chemical energy. Why chemical energy? They are chemical substances. What are they saying? They're saying that the chemical energy the chemical energy must be converted to another form of energy. You'll find this exact statement in a textbook called Hayes. Hayes is the best textbook of physical chemistry. Hayes, it is called Hayes. Anything you find confusing from the teacher, from a pamphlet like our notes, go and get that textbook called Hayes. It is the best textbook it is the best textbook of chemistry. Let me show you the cover. Those who may need it. You may need it in the future, especially those of you who are going to join campus and you're doing chemistry anywhere. Those are books you need. So they on my screen, are you seeing that part of, let me show you where is chemistry work. Are you seeing where we have revision and e-library? This is the drive that is supposed to be accessed by premium students. So when you go where you're seeing e-library, that's where you find all books. It's an electronic library. So are you seeing where you're seeing physical chemistry? So when I go there, are you seeing where you're seeing physical chemistry textbooks? You go there, the books are there. There is a book called Philip Matthews. There is a book called Holderness. There is a book called Hayes. There is a book called Brown. All those are books of physical chemistry, but please choose one. Those are different writers, but when it reaches marking, whichever those people talked about is marked correct. However, there are those they harmonize. But whichever book I uploaded on the drive, the moment you pay and access it, you get all these books. But please choose one, not all. Personally, I prefer Philip Matthews because it is wordy, so it gives you the exact things. But Hayes is a very simple book with correct work. It is good for students. Hayes. So you find these exact statements in those books. They're the books I used to write my notes. Yeah. So you choose one. Don't go for many books. It is not wise. Okay. Now we proceed. They're saying, hope our screen for thermochemistry is back. So they are saying that the chemical energy must be converted to some other form. That is something I explained. Must be converted to another form of energy for chemical substances to do what? To do work. The form of energy to which chemical energy is converted is heat energy. I said that. That's why the topic begins with the word thermal energy, because of that. Okay, let us also read this and see if we can find something interesting. Heat is a form of chemical energy associated with motion of blah 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 blah. The moment they say kinetic energy, then motion should not confuse you, because potential energy deals with things at rest, and then kinetic energy deals with what? Things in motion. Babazi, Joy, leave my screen alone. And you all know from laws of diffusion that we shall always have transfer of energy from regions of high temperature to those of low temperature. That is just obvious. You people doing biology, osmosis and those things. We always have that gradient from regions of high something to regions of low something. They are saying the heat evolved by a chemical substance can be used as a measure of the chemical energy liberated. All those statements were said. So this is the statement I want you to see. They are saying the change in chemical energy of a chemical substance is measured only if the substance is treated in a certain way. For example, when it is burnt in oxygen. That when you leave your sodium to just be there as sodium, you cannot notice a change. A change should come after a reaction. It should come after you've treated your chemical substance in a certain way. Maybe burn it in oxygen. Maybe add some water to it. Maybe add a drop of an acid to it. maybe heat it and then pass chlorine over it. That's when you notice and be like, oh, this has happened. And you'll be like, yeah, it has. And it's done. Okay, we proceed. What are they saying? They are saying something important here that I'll need to explain later. I'll need to explain later. Oh, let me hint something about it. I want you to listen. Note. I need a chat secretary. I'm seeing people writing a lot of messages in the chat. I don't know anything that needs my urgency. So assume we want to bond we want to bond A and B. What do we really do? You listen. We want A to bond to B, isn't it? This means this is the word I want, that we want to form. We want to form a bond between A and B. You get? So the word form is very important, eh? Formation. So assuming we finally form it, I don't want to ask the question now. So assume we are successful. So assume we are successful and the bond is finally formed. Now, me, the same person who wanted to form the bond, I now want to break it. I'm the same person who wanted to form the bond and I've been successful, it has been formed. Now I change my mind and I want to break. So I'll write and say that what if I change my mind to break the bond? And this is how things will be. This will be my A. This will be my B. And what do I want is to break this bond. And when I break this bond, this is what I expect to come out. Expect A to be alone and also B to be alone. They are now separate because the bond that has been joining them has been broken. I want you to follow up. Yes. So this red line, the bonds are broken. I don't know whether something that breaks is called a break. Whether it's called a breaker or a break. That's not our concern. So I want to ask people, I'm having two cases here. I'm having this case, which is case 1, where the bond has been formed. I have this case of mine here, case 2, Who is writing in my screen? Colin, you remove the things you've put in our screen. Collins, remove the things you've put in our screen. Thank you. So I'm having that one, case 2. I want people to tell me of case 1 and case 2. Case 1, I've been forming a bond between A and B. Case 2, I changed my mind, like women. I broke the bond between A and B. So what happens? These ones are now separated. So I want to ask, of case 1, which is forming a bond, and case 2, which is breaking a bond, you listen. Where do you think heat is needed? Where do you think heat is needed? Is heat needed as we are forming a bond or as we are breaking a bond? I want to see people in the chat roaring. I'm seeing people saying in the chat, inbox me, inbox me. What are you really asking? Eh? Is this a lesson or it's a dating session? Someone is like, all. Ah, some of you are not easy. Okay, so here it's very obvious that if you are to break a bond, that's when you may need heat because you're breaking. Even when we just put it in normal life, if you really want to break something, it may need you to use energy. Yes, to break something, you may need energy, but this is chemistry. We are using the form of energy as heat. So to break a bond, we need heat, energy. And that's what I wanted you people to realize. Yeah. So the mere fact that to break energy is needed, but that is English. Someone can say energy is required, that is science. But the best word to use is energy is absorbed, and that is chemistry. So you tell your parent, are you aware that when you say energy is needed is English? And are you aware when you say energy is required is science? And when you say energy is absorbed, that is the real chemistry. They say no. Tell them, don't ask me for results again. You are also not reading. Okay, now that means it is the opposite. Eh? It is the opposite. Eh, then that means if you really want to form, things are different. So we have said here the energy is what? Is heat. So the opposite is true. And what is that opposite? That for you to form, it is instead evolved. If you don't say evolved, you say given off. etc. You understand? It is evolved, it is given off, heat is released. Oh, those are very good words. Heat is what? It is released. Evolved, released, given off, needed, required, absorbed. So I want you to take that screenshot as I take you to our notes. As I take you to our notes. So you people, our notes will not be ready this holiday. It is not possible. But when you people go back to school, we shall work on them. And those notes shall be ready next holiday. Yes, and hard copies will be delivered to the premium students. Yes, you pay for premium, we send you the book. You pay for premium, we send you the book. Not sending you soft copy. Even if you are in Gulu, we have most buses that go to those regions, northern, western, eastern, and western Uganda. So when we go back to our notes, just read through. This statement will now make sense, but before it wouldn't. They are saying that every time things are reacting, there are bonds that are always broken and there are bonds that we always form. Of course, the bonds that break are the old ones. Those that they form are the new ones. That is now just English. Yes. And of course, the ones we break are in the reactants because reactants are the ones that get involved in the reaction. Then there's those that we form, of course, they're in the products formed. You understand? The mere fact that you formed a product, that means that the bonds within the product have just been formed too. So they are new. That is just English. And what is the conclusion? The conclusion is that energy is absorbed to break the bonds, and energy is given out when new bonds are formed. I don't know whether those are those who know some Luganda, but the good thing, all of you are Ugandans. All of you are Ugandans. And I want to give you this simple mnemonic. All of you are Ugandans, and you know that our president has been on for some good time and is the next president. So someone may make a compliment. Someone may make a compliment about bonds and say, hey, those people can rule. That's what they say in English. You'd be like, this president has overruled us with his people. So you'd be like, those people have actually ruled us. So for us during high school, back then in 2018, they used to, 2018, 2019, they used to say, in Luganda, if we convert that statement, we say, um, abasajja. Abasajja are men. Abasajja bafuga. That those men have actually ruled us. So you'd be like, abasajja bafuga. I've taught you how you can learn it, but there are people here who are good at mastering mnemonics. So where I have a mnemonic, I'll give you. But literally in my dictionary, I have very few mnemonics. So basajja bafuga, what does that mean? That when, remember it is about bonds, yeah? So this is about breaking. Then this F is about forming, yeah? This F is about forming. What are you forming? We have said bonds. What are you breaking? I've said we are breaking bonds. So it is easy. When you break a bond, it is what? Absorbed. Ah, breaking bonds, you absorb heat. What else? What is this gift for? It is given out. Mm, yeah. But you know the real chemistry? This is now local. But you can have it. Basajja bafuga. That is that. So that word is bafuga. Okay. Now, after us appreciating about the heat and everything, it is very important you find information about this. We are going to talk of the heat content of a substance. Get? So you have said every chemical substance, so the word chemical is lacking there, but I will edit and add it, has some chemical energy stored. And when a reaction takes place, we shall have that conversion from the stored chemical to the heat energy. What are they saying? They are saying don't generalize these things. There are levels to these things. How are levels in these things? That the heat content differs from one substance to another. Why? The molecules of different substances differ in the number and type of atoms and the number and types of bonds between them. You know that people are getting it. What they are trying to mean here, that they are alkenes which look like that. They are alkenes which have something like that. They are alkynes which have the triple bond. We have carbonyl compounds which have such a bond. We have alcohols which have such a bond. We have amines which have such a bond. We have nitriles which have such a bond. You get the point? That's what they meant. Even alkenes, you know that alkenes and alkenes, alkynes have that bond somewhere. So that's what they are saying. That you cannot tell me that you need the same energy to break all those bonds. Never. Yeah, that's why they mean by the heat content is different. So for us, we are going to take it in the form of breaking them. Assuming they tell you to break all these bonds, you may be like, this one is a single bond, so it may need the same energy with this single bond. But you're forgetting that this first single bond is carbon to carbon and this one is carbon to oxygen. So because of the difference in the type of the atoms, this is carbon, this is oxygen, you cannot require the same heat. Even when you say that, if you have refused the atom, let me say that since this is carbon to carbon, let me just put a square. Someone may be like, since this is carbon to carbon, and also this is carbon to carbon, then they need the same energy. Never, that one cannot happen. It can't. Because these carbons have a double bond between, and these ones have a triple bond. A triple bond is harder to break than a double bond. So the heat content can't be the same. Collins, remove that line. Don't disorganize me. So you get the point. So single bonds, you cannot be like, this one is carbon to nitrogen and this is carbon to nitrogen. So they need the same. Never. Never. This one is triple. This one is double. So heat content can't be the same in terms of that needed to break the bonds. Even this last one. So to end with, you look at this in purple. Carbon to oxygen. Even this is carbon to oxygen. So don't be like, my dear, this is double, this is single. Get the point? Yeah. Don't say single bonds are the same everywhere, provided it is single. And maybe one point you want to break this bond, carbon to chlorine. And be like, you are joking. This is a single bond and this is a single bond. They need the same energy. That one can never happen. Why? The atoms are different. That's why they even talked of the number and the type of bond. That the bond may be double, another time triple. Something may have 4 bonds, another one may have 3 bonds. So you have to respect that. One can have 3 atoms, another one can have 200 atoms. So the energy content can't be the same. Hope you people are listening and following. Now, the very first term that we are going to look at today is the term called enthalpy. Enthalpy. Let me tell you, people can't. If at all I have someone here with a tooth gap, if I tell them to say the word enthalpy, they may correctly say it on Thursday with continuous trials. So it is something that is not fair at all. It is not an easy word. So enthalpy, we have talked of these chemical substances storing some energy. You understand? So the total energy these substances are carrying, the total energy content of a substance, the total energy these substances actually carrying, they're actually storing, the total is what they call enthalpy. I don't want to hear people saying enthalpy. It is enthalpy. Enthalpy. The Baganda who are on, there is no U here. And this is letter Y, not letter E for the Baganda. So I don't want you to be like Dr. Utaya, lero yatusomeseza enthalpy. It is enthalpy. That is the right word. How is it denoted? Symbol H. Capital. Someone may be like, why H in all letters? Because the topic we are handling is thermochemistry, and thermo means heat. So when we talk of total energy content, that energy we are targeting, that form of energy we are targeting is heat energy. So we give it that capital letter H with respect to the word heat. So I don't want you to have small h. It is basically that. So let me give you a chance to take a screenshot for that page. We are done. We are done. We are done. We are done. Take the screenshot after the class. Go through the notes. Hayes is our textbook. Those who need the email of Hayes, I think I'll give it to you. Hayes is still alive, but he's 72 years. And next week on Wednesday is going to have a webinar. A webinar is a seminar which is online via the web. It's going to talk about chemistry and AI. Chemistry and AI. I think it's going to bring something that is better than PHET. Yeah, those are simulations that I always talk about. So on Wednesday night, Thursday morning, next week, make sure you ask me what Hayes said as far as chemistry and AI is concerned. This is what we are going to handle next. So we have looked at what enthalpy is and what enthalpy actually means. Okay, now enthalpy change. Enthalpy change. Remember enthalpy alone. Those of you who studied differentiation with me, who studied differentiation with me, I remember telling you that taking pop theory, I beg you behave. You're writing in my screen. You people, you cannot have taking and also having discipline at the same time. So as a user of that phone, we expect a lot of discipline from you. I think the last time I had that phone has a tendency of becoming too hot. I think I had my picture on the wallpaper of the screen. The phone became too hot and even the picture started sweating. That's when I think I had to set it off that very day. So those who recall the topic of differentiation, we talked of changing y over changing x. Those who recall, we said you can write it as dy dx Remember telling you you can use those symbols, the Greek letter delta, but standardly it's always that minimized triangle. You get? So basically in science, those minimized triangles mean change. So basically those minimized triangles mean change. So when I say enthalpy, you know enthalpy is this H. Then when I add on the word change, I also bring this K1. Now the Baganda like, if it is enthalpy change, why don't you say enthalpy then change? Oh, don't disturb us. It is always, okay, the word is enthalpy change, but the right English is change in enthalpy. So change in enthalpy. That is the symbol. So what is this? I don't know whether people recall that I said the content of the substance cannot change. But if you really want to notice a change, then take away mbeda. Put a situation. Put bring some pressure. How? Burn it in oxygen. You understand? Add water to it. Add there an acid. You understand? And you all know that most reactions in chemistry take place at what they call standard temperature and temperature, most of them. But this is what I want you to learn, that if we really want the heat content to change, for heat content to change, I repeat, it should only be after ng'otaddewo embeera. If you really want your work crush to give you some green lights, also put there some situations. Ask her what the day today is, ask her the time, but I'll tell you that later when we shall be revising some topics next week and how you're supposed to survive in A level. I'll tell you all those tricks at the right time. Right now I have some moderators on. I don't want them to give a bad report about me. Okay, where are we? For us to say change, a reaction must take place. Why am I telling you that? That this word during a chemical reaction is very important. You people were doing the new curriculum in O level. You realized that nowhere you were not even asked at any one time to define. That's what we expect at A level, but we are still waiting for the form of assessment. You may be asked to define or you may not, but you need to know what things mean. So, meanwhile, I don't want you to be so stressed about cramming the definitions exactly as they happen to be, but have the understanding. Just the understanding. The moment the form of assessment is out and definitions are part, then I'll come here and I'll tell you that, my dearest, definitions are part of your assessment. But meanwhile, have the meaning and go to the next thing. So, enthalpy change during a chemical reaction should appear. But we've said most reactions in chemistry take place at STP. STP is standard temperature and pressure. That is the STP. That's the full form. Abbreviation STP. You understand? Yeah? But the other word remains. The other words remain: heat content of a substance. Just two words come in: chemical reaction, because that's when a change happens. And reactions in chemistry mostly take place at STP. Exactly. So they are giving you another word, that enthalpy change is the same as heat of what? Reaction. And because of the word reaction, we can add on the short form of reaction as a subscript. So get it from me. The word RXN, this RXN, it is a standard abbreviation. So it's not just there for fun. It is a standard what? It is a standard abbreviation. Heat of reaction goes with change because a change happens during a what? A reaction. Now, this is a problem. This is a problem. I think this definition is what we are going to talk of next. But before I even talk about it, I want to let you know that if they don't call it standard enthalpy change, they can call it standard heat of a reaction. They can also call it standard enthalpy change of a reaction. But when they add on of a reaction, it may be a repetition. Why? Because change only happens during a what? A reaction. So someone may be like, but we have just defined enthalpy change. This one is just standard. What is so different? What is really so different? And I'm going to tell you that. But I want you to appreciate one thing before I proceed. That when it becomes a standard, we add on a theta as a superscript to show the difference. Hope we are together. We add on theta to show what? Standard. And the theta should be a superscript. I can say a power, but superscript is better. So when I take you here to our book, I'll give you a note that H alone is enthalpy. Change in enthalpy is just like that. Then standard change in enthalpy, because of the word standard, we put that theta. And I'm going to tell you what all those mean. But if you are told we want to be so specific and say heat change of a reaction, because of the Coward reaction, we can decide to add there our subscript as RXN, a standard abbreviation. It is very okay. But I want to give you the cheat code. I want to give you the cheat code that is going to dominate this topic. Cheat code. What is that cheat code? What is that cheat code? Every time every time they say standard, every time they say standard, they mean yes, Mbabas, you speak as I also write. They mean
Increase on your voice.
it is your device. But for you don't greet, you just unmute and complain. Some of you are very indisciplined. They mean that whatever is happening, whatever is happening is doing so under standard conditions. How can you say increase on my voice? You people, this is online. Even if I talk slowly, you will listen. That one depends on your device. But at least you greet, eh? They mean that whatever is happening is doing so under standard condition. Is doing so under standard what? Conditions. That's the major thing. So someone may ask, what are these standard conditions? The standard conditions are two basically. We have standard conditions of temperature. Remember, basically in this chemistry of A-level, temperature is preferred in kelvins. So the standard conditions of temperature are basically 298 what? Kelvins. And then the standard conditions of pressure standard conditions of pressure are basically 1 atmosphere, abbreviated as ATM in small letters. ATM, something like that. Standard conditions of temperature, those ones. Standard conditions of pressure, that one. Hope we are together there. So you're going to realize that every time you're going to see the word standard in this topic, you see somewhere people quoting this 298 kelvins and 1 atmosphere. But you should know that those are the conditions of what? Standard conditions of temperature and standard conditions of pressure. So I don't want your teacher at school to tell you that the standard conditions of temperature are 25 degrees Celsius. Then you'll be like, that is wrong. They told us 298 kelvins. It is the same thing. Even pressure has some other values in millimeters of mercury and everything. But these are the basic two, yeah? That, and it's what we shall always use. But if you feel like those words are very hard, and by chance your curriculum wants us to define, we shall always be using the word standard conditions, yeah. That whatever is happening is doing so under standard conditions, full stop. If you want to be so specific, we say at 298 kelvins and 1 atmosphere. Okay, now people, sorry for that. People, sorry for that break. Yeah, I had stopped a bit for 1 minute just to fear women. Then I get back and I'm back. Hope my local people have not been disorganizing the room. Okay. Standard. I've just said every time they talk of standard, expect 1 atmosphere and 298 kelvins somewhere. You like it or not. You get the point? But since we are talking of all reactions in chemistry, this is the general definition. That's why immediately after defining it, we are going to go to other things. Those are types of heat of reactions. Yeah, and they are the easiest. So I want to write some reactions here. Those who attended with me chemical equations and something, I want 3 reactions only that require balancing. I need a good chemistry student here. I want a good chemistry student here to give me 3 reactions they know that require balancing. Any 3. Please, Adasha, you leave our screen. Now, who is this Adasha? Please, I don't want you to expose your inferiority and primitivity here. Please. I said you raise up your hand. Okay. I want 3 reactions in chemistry. Yes, Emmanuel?
We can use ammonia and copper 2 oxide.
You can use what?
Ammonia and copper 2 oxide.
You give me now simple reactions. You tell me
Okay,
nitrogen and hydrogen to form ammonia. Ati yonjaga
nitrogen,
zaki.
hydrogen form ammonia, then oxygen plus hydrogen form water.
Such reactions. It is not a battle. You also want me to start saying weird reactions here.
No, it's okay. And then maybe sodium hydroxide and HCl. No, and sulfur acid and sodium hydroxide.
Okay, thank you, Emmanuel.
Welcome.
So you people, I want to show you something and I want to teach you something. Eh? Those are just sample reactions. I don't want people to start asking me, why this, why this, why this, why this, why this? Okay. So I want you to look at this. Nitrogen is a gas, you all know. Hydrogen is a gas and ammonia is a gas. And we all know for this reaction to proceed, 1 mole of nitrogen gas should react with 3 moles to give us what? 2 moles. So I want to teach you that the 1 mole and 3 moles reacting, those are what they call molar what? Those are what they call molar what? Molar quantities. Then here we also know 4 moles of sodium should react with 1 mole of what? Oxygen to give us sodium hydroxide. And we all know this 4 is a molar quantity because we said 4 moles, and the 1 mole is also a molar what? quantity. And we all know sodium is a metal, so sodium is a solid. You get the point? Zinc oxide is a solid. Now this is hydrochloric acid and it is aqueous. These are things I gave time in that topic of chemical equations. So I don't want you to be stressed. Then zinc chloride is a solution, and you all know the water is like that, and the water is a liquid. And that is the standard state of water. So I want you to realize here it was 1 mole of what? Zinc oxide, and these were 2 moles of hydrochloric acid. So I want to bring something to your attention, that 1 and the 2, they're what they call molar what? Molar quantities. Definitions in A-level chemistry are too many. So the chances are high that they are going to bring back these definitions as a form of assessment. They will have to bring it back. Okay. Now, the other thing I want to talk about is that these things you're seeing, the gas, nitrogen is naturally a gas. So we had gas. Sodium is naturally a metal, so we had solid. Water is naturally a liquid, so we had liquid. Acids are naturally aqueous because they ionize in solution. That's why we had aqueous there for the HCl. So I'll put there aqueous. So all these states you're seeing, the gas, solid, liquid, and aqueous, are what they call standard what? Standard states. Please, Team K, you leave our screen. We call those standard states. So when you look at this kind of reaction, we are having reactants in their standard states with the rest, and their molar quantities are also present, and they are giving us the products they are supposed to give us. That's what they call a reaction in chemistry. That reactants in their standard states, or you find some people calling them normal physical states. So don't be confused when you go somewhere and they are calling them normal physical what? Normal physical states. It is very possible. Or standard states. Then the molar quantities are those balancing factors, and they are giving us the products they're supposed to give us. And for us to say that this is actually standard, we agreed that standard means things are happening under standard conditions. What are standard conditions? 298 kelvins and 1 atmosphere. So let's read the definition together and see if it actually makes sense. Okay. Let's read it. It is saying this is the heat change. Of course, it is a change. When does it occur? It occurs when molar quantities of what? Of reactants. These reactants, where are they shown? In a well-balanced what? Equation. You understand? For a reaction where they are in their standard what? States. And because of the word standard, that is denoted with a specific theta as a superscript, we have these conditions of 1 atmosphere and 298 kelvins. People, is that definition hard? But the moment molar quantities of reactants, as it is clear in a balanced equation, and these reactants have their standard states or their normal physical states, and everything is occurring at 1 atmosphere and 298 kelvins, the heat change that has actually taken place is what they call the standard enthalpy change of a reaction. I don't know if you people get what I'm saying. Hey. Then, you just comment in the chat. Definition is okay, definition is okay. The curriculum urges you to understand the meaning, but not cram the definitions. But what if definitions are part? Why would you even cram? You understand. what the definition actually wants. Period. So, is the definition okay? Is the definition okay? Then you people have not been following. Every word in the definition has been explained. Eh? You people have told you. You look at that. Molar quantities are those balancing factors. The standard physical states are there. All those equations are balanced. Because of the word standard, everything is taking place at what? 298 kelvins and 1 atmosphere. So when the reaction takes place, a certain heat change occurs. Heat change meaning that when those reactions occur, we are either going to have heat being evolved or heat being absorbed. So that form of heat evolved, heat absorbed is what they call the heat change. People, I remember telling you that generally the word is heat change, but the change can be evolving, the change can be absorbing. And that's what they are just converting into English here. That the heat change is occurring when what? Molar quantities of reactants shown in a balanced equation for that specific reaction. And these reactants are in their standard states. React completely at those standard conditions. Yeah, if you have not gotten it, you just have bad manners. So before I hear from, okay, let me hear from Raymond. Yes, Raymond, what do you have to say? So they are saying the standard state of a substance is the phase. Remember telling you that, that these things of solid, liquid, gas, they are phases.
Sir, you have talked about standard states, but it's also zinc oxide in its standard state. I'm still confused on the other thing with the equations.
Zinc oxide is a solid. You get? Yeah, so it's in
Yeah.
its normal physical state. Standard means normal physical state. I said that. So here they are saying it is the phase in which a pure substance, by pure they mean nitrogen as nitrogen with nothing else, hydrogen as hydrogen with nothing else, oxygen as oxygen, nothing else, water as pure water with nothing. The phase in which it exists is what they call a standard state, or is what they call a state. But because of this word standard, we add on standard conditions, which is 1 atmosphere, abbreviated as ATM, and 298 kelvins. Just understand what the definition means and move on. You get the point? Yes.
Yeah. So I ask another question.
Yes, sir.
Okay, sir. But I thought like the thing of standard states is as if it is a zinc in its normal state, not like zinc oxide, because zinc oxide seems to be like as if it's a compound.
So you tell us, what is the standard state of zinc oxide?
It is a solid, of course.
So what do you want? And what did we put?
Yeah, I've got it, sir. Thank you.
Okay. Yes, Chimbugwe.
Sir, is aqueous state also a standard state, or for it is not a standard state?
The aqueous falls under the liquid phase. You understand? I've told you the phases are basically three: solid, gas, and liquid. So aqueous falls under the liquid phase, but it is also its own physical state. You understand? You ask, you mute. So what do you want me to do for you? Okay, people, let us go. So I wanted to tell you that basically heat is measured in joules. Joules, and I know people know that. We joules have the short form as capital J. You understand? But you people, just like kilograms, I'm going to ask something interesting. So just like grams and kilograms, we have joules and kilojoules. Kilojoules. Now I want you people to expose your primary schools in the chat. I want you people to expose your primary schools in the chat. By the end of what I'm asking next, we shall have told who started P1 from home, who started P1 from Taiba, who started P1 from Aga Khan, who started P1 from Sapporo Kagwa, and then other schools. Our village schools, Tendo Primary School, St. Valley Kudembe, Agali Awam, and those schools of chairmen. Of these two, which is correct? Kilogram. You write it in the chat. The difference is on the K. This is capital K, this is small k. Which is the right kilogram? You just write it in the chat. I want to see. And there is a people who started from home are very fast. I don't know why. Such schools, St. Jude Primary School, Hoima. You cannot have a correct form of the word kilogram. All of you have failed. Anyway, I like that. Even these ones who are commenting last, they're just trying to use, they are trying to use reverse psychology. So you people, you learn this from me today. Hey, at least you learn something. This is very wrong and this is the correct thing. Kilo is small k. I don't know, what do you people trust most? Do you trust most textbooks or the internet? But either way, that is it. Kilo is small k. There is a way people who studied from home are very fast at commenting in the chat. So it's supposed to be a small letter, eh? Small k. Capital K is kelvins, eh? You learned that from me. Capital K in chemistry is kelvins, and the kilo, the K, is supposed to be small. So kilograms, small k and g. Kilojoules, it is small k, but the joules is already capital, so it's supposed to be like that. Like that, eh? So the moment you see your teacher writing kilojoules on the board with a capital K, you tell them, no sir, K in chemistry is in kelvins. You ask your teacher, teacher, why don't you read the textbooks? You tell your teacher, teacher, you are incompetent. You are not reading textbooks. Capital K is for kelvins and equilibrium constants. Small k is kilo. See, teacher, you are not reading. That's why I used to like backbenchers. When the teacher writes something that is not right, that's why I may like these lessons. These lessons are good. It is very hard to get embarrassed. But in a physical class, those days in 2019, teachers used to make errors. And when the teacher makes an error and it's corrected, backbenchers start saying, cram work. All class moves out. 5, 5, 5, 5, 5, 5, 5, 5. Then we also used to come with our reasons. After seeing a girl saying, sir, you're not going to cane me. I mean, my periods, what, we also come and say, sir, I also have a problem. Which problem? I also have sperm cramps. Then they tell you for you're now going to receive 20. And they give you that very well. And our teachers were very bad teachers. After the teacher caning you 20 strokes, he takes you to the staff room and he says, this boy is indisciplined, he has refused to be caned. And then other teachers converge. You know that weird noise always in the staff room. Every teacher is just throwing a random word. And then you feel out of place. You feel like you're tired of life. Even a teacher who has never seen you is like, this boy again. Do you know those teachers? You're seeing the teacher for the first time. They are also seeing you for the first time. They take you after a crime in the staff room. They start, this boy again. Down 20. After caning, you other teachers come in, they be like, that one is indisciplined. He has refused getting caned. After giving you some random 6 strokes. Of course, people from schools that don't cane can't relate. You ask someone from Budo SS, Gombe, Mbogo mixed. Hello. Yeah, I'm sorry. Say that. It's okay. It's okay. Okay. Where was I? So kilojoules. Let me see. Heat is measured in joules, just like grams. Okay. So we have kilojoules, and that's how kilojoules are represented. Don't make an error. So this is the standard unit. This is the unit that is used always. So I'll say always used unit. Kilojoules. So it is written like that. So you are getting out of the lesson. Yeah, you leave my class. Don't stress me. How can you tell me what to do as a 17-year-old? You people don't have discipline. So you are getting out of the lesson. Is it you who told me to start it? Okay. So every time we are measuring heat changes, we have realized that equations always involve moles. Equations or reactions. They always involve moles, so that is something you should appreciate. That reactions always involve moles. So most of the heat changes will always happen in relation to how many kilojoules have you lost, how many kilojoules have you absorbed in relation to a mole. So that's why in most cases the unit is kilojoules per mole. But if someone doesn't want to write that per mole, they will write small k, capital K, joules per mole, like that. So that is the unit that is always used for thermochemistry. So when you come across it, don't ask. That is it. So even here it was stated kilojoules per watt per mole. So types of heats of reactions or chemical reactions, you all know. You all know. You all know. That we either evolve, as we said, or we absorb heat. Evolution, it can be giving off heat or releasing heat. Absorbing can be requiring heat, can be needing heat. So basically we separate them into exo and endo. So you know, exo is like exocytosis moving out. Endocytosis moving in. So moving out, the heat is leaving. So we are releasing heat. You understand? Endo, we are bringing in, we are absorbing heat. That is just obvious. Okay. So I'll come and say exothermic evolution of heat to where? The environment. Endothermic absorption of heat from the environment. You understand? So, I want to show you something here briefly concerning the types of reactions. So, assuming we are having A plus B and A plus C, they are giving us this one. Those who attended chemical equations with me, these are what they call reactants. These are what they call products. So we are going to assume they have maybe 20 kilojoules, and then they lose 15 kilojoules. Understand? If they lose 15 kilojoules, that means these products will have 5 kilojoules left. Get the point? So because reactants have or had 20 and they lost 15 to the environment. So this 15 means what? Exothermic. And you people know anything to do with the loss, anything to do with the loss, anything to do with the loss, even if it is business, a loss is considered as a negative. Even if you are in business, even if it's what, provided anything is involving a loss, negative. And we all know losing heat to the environment is exothermic according to chemistry. So here I'm going to just put and say reverse true. The reverse is true for endothermic. Reverse true for what? For endothermic. So this 20 for the reactants, I can now strongly say it is higher energy. For the reactants, then lost 15 products remained with 5. So this 5 I can also boldly say lower energy. And I may decide to add on another word and say lower energy level. Higher energy or lower energy. Or I can add on levels. Higher energy level, lower energy level. Something like that. So we are going to read the next statements, and they should make sense because of what we have here. So here the next statement is, you know that exothermic deals with losing heat. So they are saying it is denoted by a negative sign, but for endothermic with a positive. Understand? Because one is the opposite of the other. Why positive? We are absorbing, we are just getting it, we are getting more heat, but there we are losing it. So here they said, since we are losing, our products turn out to be at a lower energy level than reactants, or our products have a lower energy than reactants, which is clear here. Do you see? We had 20, lost 15, products remained with the 15. So products were actually at a lower energy level than the reactants. That has been explained. This is just an example of a sample reaction which is exothermic. They are simply trying to show you every time hydrogen reacts with iodine to form hydrogen iodide. I taught this in chemical equations. They're trying to show you that some heat will have to be evolved. And that's why they are showing it with a negative. Yeah. Then here it will be the opposite. Since you just add, the reaction is going on, but you're just absorbing heat from the environment. So by the time you form products, they will have a lot of energy. So you like it or not, products will have to be at a higher energy level than reactants. Remember we said the reverse is true for endothermic. So this equation means that when you get heated carbon and react it with steam, as the reaction proceeds, this is the amount of energy that will be absorbed from the environment. As simple as that. As simple as that. So they are talking of some interpretation here. They are talking of some interpretation here. They are saying, let's begin with this equation, the first one, this one. They are saying 1 mole of hydrogen reacts with 1 mole of carbon, reacts with 1 mole of carbon. What is this? You ignore this statement. I think I'll need to edit it in the notes. But this is what they are meaning. 1 mole of hydrogen reacts with 1 mole of hydrogen to produce 2 moles of gaseous hydrogen iodide with evolution of 9.2 kilojoules per mole. Then for this one, 1 mole of carbon reacts with 1 mole of steam to form 1 mole of carbon monoxide and 1 mole of hydrogen gas, with absorption of 131.4 kilojoules, period. I don't know if that is okay, because what is coming after here is something different. Something different. And before I explain it, people, you take that screenshot as you also let me know whether the two types of reactions are okay, endothermic and exothermic. All those statements on them, are they okay? Let me tell you, it is the introduction of thermochemistry that matters. When you understand all these simple meanings, surely it will help. So you take that picture, yeah. So should we go to the next thing? So you people, there is this battle. There's this battle between A and B to give you C and D. Then there is this battle between W and X to give us Y and Z. That is the battle. What is happening? A and B are saying that for us, we release heat, we release heat, we release heat as we form C and D. That's what A and B are saying. Then W and X are saying, for us we need heat. We need heat to form Y and Z. Yes, I want this question to go to women. Let me ask my question. Yes, Michael Bray, as I write my question. Michael Bray, you have refused to unmute. Sir, do you recommend us to use demystifying chemistry? It's a pamphlet. Die. The people. A senior for graduate is calling someone's book a pamphlet, not a textbook. For you, where is yours? Hmm? Let me see the name of that boy. Yes, Blair.
Okay, sir. Good afternoon.
Hmm.
So, my concern is here you have put like done for W and X. Instead of you putting we need heat to form Y and Z. You have pressed we need heat. We need release heat to form. So that's the only thing. The release this side. Yeah.
Oh, thank you.
Okay.
You people, you stop undermining people's books. Yes, yes, it is a pamphlet, but of course someone put in energy and they wrote it, so they are good books. But you're supposed to use it in line with your syllabus book so that you can easily look at what they want and what they don't want. Yes, people have awards for those books. People have awards for those books. So don't undermine people. Anyway, where are we? You people answer this question. It is for women. It is for women. So you're approached by two boys. One boy tells you, if you want us to be in a relationship, you're supposed to give me money. Then another boy tells you that if you want us to be in a relationship, I'll give you money. So which one do you go for? So A and B are like, for us to give you C and D, we shall release heat. We are just release heat. We don't need heat. But W and X are like, for you to get the Y and Z, you're supposed to give us some heat. Provide some heat to us so that we can collide and Y and Z get formed. Something like that. So which one do you think is more possible? Which one will occur first? Which one is likely to occur? Which one is more possible? People tell me. Yes, Tracy, with the reason.
Teacher, me, I think it's A and B to produce C and D because,
Mm,
like, A and B, it needs less energy, like, to give out more than the W and X that needs more energy to absorb.
oh, so you'd also are you still on? Why are you muted? People, why you disappear just like that? Just raise up your hand again.
Teacher, I'm on.
Oh, so what I wanted to ask, so
Yeah.
if you also have two options, a man without a car and a pedestrian, you go with that one with the car.
Yes.
So where do you park your car? Where do you park yours?
Teacher, in the car, like in the parking lot.
Okay. Now, yeah, she's right. I think this first reaction, A and B interact to give, then they release heat. This one doesn't need forcing. This reaction is not forced. You understand? But literally, W and X need heat. So you need to force this. This one must be forced to actually happen. Yes, it must be forced. But the other one doesn't need forcing. So you like it or not, it is that of A and B. This. It's what that is most likely to occur because it doesn't need forcing. Hey, things will occur on their own with no pressure. And why am I bringing that? I'm bringing that to bring the point of hence. Remember A and B, it is exothermic. Those who know the terms very well. Because they release, it is exothermic. And here, because they need heat or require heat, it is endo what? Endothermic. It's one exothermic, something like that. Exothermic, endothermic. Now, people have now realized that exothermic ones don't need to be forced. But endothermic, we fail to provide it, they will not proceed. So they are last bonds here. So hence, exothermic reactions exothermic reactions exothermic reactions thermic reactions are more possible or more likely to occur than what they call endothermic reactions than what they call endothermic reaction. Than what we call endothermic reactions. Now, there is what they call the possibility of a reaction, just like I've said, that the exothermic ones are more possible. So possibility is an English word, but we are dealing with science. And the word that is synonymous to possible is feasible. You understand? So we are not going to use possible again, it will be feasible. So possibility of a reaction is its feasibility. So the moment they ask you which of the reactions is more feasible or just feasible, they're asking for that is likely to occur, more likely to occur, possible, more possible. Hope you get the point. So we are going to read that note together in the notes and see what probably the writer had to say. Look here. Look here. I want people to tell me the statement is okay. They are saying the sign of the enthalpy change is an indicator of its possibility. Here they are using feasibility, but what have we said? Feasibility is for what? Possibility. And what are those things? The likeliness to occur. Is it likeliness? Likelihood. Likelihood to occur. What are they saying? That the more negative or the more exothermic, the more heat given off, the more negative, the more exothermic, the more heat given off, the more heat evolved, the more heat released, the more the reaction is likely to be feasible, the more the reaction is likely to occur, the more the reaction is likely to be possible. This is a statement that most of you didn't know, or most of you didn't know that it is very important in the topic. So is that statement okay? Just need to combine it with these. Just need to combine it with those notes. Is the statement okay? No negative, more exothermic. That means we are not going to overforce it. So chances are high that it's what will occur. For the first time, people have maintained the numbers. That means I'm going to start teaching in the afternoon. Because at night, the moment you go into around 2 hours, people start going off. Okay. So you can take that screenshot. I don't know if we had it. That one. We had that one already. So what is next is today's thing, this energy level diagrams. Energy level diagrams. And this space is for them. I haven't put them in my book, but I'm going to put them here. Yeah. So let's draw the energy level diagrams. I'm going to start teaching in the afternoon. I don't know that people actually concentrate for such long hours during day. I thought people prefer nights. So I'll be teaching during day, then in the night, if there is no biology, then you visit work on the drive. Also, I'm talking to the students who will be with us tomorrow. God willing. Okay, let's draw the energy level diagrams. They have the most marks. Yes. Should I draw them here? No. So I'm going to begin with a reaction that is exothermic. So I'm going to begin with a reaction that is exothermic. So this is it. I want to have some sort of exothermic reaction versus endothermic reaction. So I want to teach you something. When you say that you want A and B to react, I want you to listen If you want A and B to react, maybe assuming we are having this line which shows the energy level. Slowly, I don't want to panic. I don't know. Let me begin with the exothermic reaction alone. I think it will be better explanation. So assuming I'm having that line, just showing energy level. Now, I have my A and B. And I want these ones to give me C and D as we have been doing, isn't it? Now I want you to understand something. That in chemistry, before reactants react, their name is reactants because we expect them to react. But they are saying that before they react, they must attain, a minimum amount of energy. Why minimum? Because it is the least they will need to react. I want you to listen. That in chemistry, before reactants say that now let's react to form product, to form a product or to form products, they must attain a minimum amount of energy. Are you listening? That A and B are intending to react. But in chemistry, before that reaction takes place, a minimum amount of energy must be attained. This energy activates them. This energy activates them and they finally react. To form, I'm going to show you what they form. But I want you to listen. That A is alone. Look here. Somewhere here. B is also alone somewhere here. For them to react, they first look at each other and stay and wait for a certain amount of energy to be obtained. And it is a minimum. Minimum because it is the least requirement for the reaction to proceed. Are you listening? Minimum because it is the least requirement for the reaction to what? To proceed. Now, as they look at each other, the moment that minimum energy is reached, what they call the threshold, what happens? They touch each other like that. Because they are going to react. Remember, they have been separate. When the minimum amount of energy has been attained, they have been just looking at each other, now they touch. You understand? They touch. And when they touch, they are now active. You get? There they have been just alone looking at each other, inactive. But when they finally touch with that dashed bond, they form what they call an activated complex. You get? Activated complex, because that minimum amount of energy has activated them to now finally react. You get the point? So it is this activated complex that will later split to now give us the product. I know most of the schools have done enzyme action. Do you know that thing of enzyme where the enzyme first looks at the substrate, then later they form enzyme substrate complex after they are together. Then when the substrate leaves the active site, you call it now a product. You understand? That this A and B, they have been just looking at each other as they are attaining energy. The moment the threshold or the minimum is attained, they are now activated and they can now give us the products. How do they get activated? They touch each other. How can you show that? With a dotted bond. How do we call that? An activated complex. And this can later give us products. So you can look at this as enzyme and substrate looking at each other. This one, enzyme substrate complex. This one are the products. If you don't do biology, ignore and get the real chemistry, just like it has been explained. As simple as that. So learn it that before reactants finally become products, they pass somewhere, and that somewhere is the activated complex. So what do I want to say here? I want to say that this thing they are calling the minimum amount of energy they need to get activated and later react is what they call activation energy. That one is called what? Activation energy. Called activation what? Energy. That is it. Then the other thing I may add on, that some people, especially those who read a lot of textbooks, you will find that the activated complex, they can call it the transition state complex. Someone may be like, why do they call it the transition state complex? Simply because we are going to have a transit or a transformation from reactants to products, but via that complex. So it is a complex of transition, transformation from reactants to products, and for it, it is somewhere there in the middle. And we are going to show all that. Now, lastly, and most importantly, if you're having A and B and you expect them to give you C and D, this one is our target reaction because it's what we have been basing on. So we call it the forward what? So we call it the forward reaction. I told you reaction, RXN, is a standard abbreviation. See that? Then if we happen to realize that C and D can react again to give us C and D, this one is now called the backward what? Reaction. And those are standard terminologies in chemistry. A and B giving you C and D, if it's your target reaction, it's the forward. The moment the products can give you back the reactants, now that one becomes a backward what? Reaction. Forward reaction, backward what? Reaction. So when you read terms like activation energy of backward reaction, I don't want it to confuse you. I don't want it to confuse you at all. Then the other thing, remember when we said that products may be at what? 20 kilojoules, isn't it? Right, kilojoules really, 20 kilojoules. And then these products of ours end up at 5 what? Kilojoules. I remember we said something important here, and what was that? That we have lost 15 kilowatt, 15 kilojoules have been lost. So what has been lost is actually the change that has taken place. You understand? That the reactants were at 20, products were at 5. What was lost? 15. So that 15 is what they call the change, the heat change of the reaction. Heat change, or you can call it enthalpy change if you have been following our definitions. If you don't say heat change, you can say enthalpy change of the reaction. And you people know how it's denoted. Change in heat energy. And if it is standard, you know where we put the theta. So trust me, this is all you need to do the energy level diagrams. Because at least I know that you people can deal with exothermic reactions, and you the same people can deal with endothermic reactions. You understand? So very first, I'm going to put here 2 sketches. I'm not going to write what we already have. Then put here 2 sketches and then we match. So we are going to do some matching. I'm going to have something like this. I'm going to have something like that. Now, these energy profile diagrams, this is how they are supposed to look like. They are supposed to look like. They are supposed to look like that. Eh? So what we always have here are reactants. Then in the end, what we always have are products. Same thing, what we always have here are reactants. Then what we always have here are what? Are products, you get? And then you people recall what we said. I don't want to talk about it now, but I want us to concentrate on the energy level. So here, at this point, this is case 1. This is case 2 here. For case 1, are you seeing this level? Is the energy level of the reactants. Then for products, are you seeing this? Are you seeing there? It is the energy level of the products. Remember this arrow, we agreed that is the arrow that is showing us the energy level. We can call it potential what? Potential energy. And you know the unit we agreed, it is kilojoule small k per mole. You understand? Hey. So even case 2, at that level, it is for the reactants, then products, there like that. It is energy for the products, like that. Reactants, products, reactants, products. So I want you to realize that for this first diagram, remember these are just sketches, eh? The energy level for the products is greater than the energy level for the reactants. Then for this one, the energy level for the reactants is greater than that of the products, isn't it? So I want you people to tell me of case 1 and case 2, where do we get, or where are we going to find, or which one is for the exothermic? Where is exothermic? Case 1, case 2. Yes, Tracy, with reasons.
Exothermic is case 2.
Why?
Because we said in exothermic, the products lose heat to form the products. That means the products will have less heat than the reactants.
Exactly, yes. So thank you for that. And that's what we said. That reactants will lose. So that means the final product that will come out will have less energy compared. Do you understand? That reactants had their energy 20. As during the course of the reaction, we lost 15. And the products were found to be at 5. That's what they call exothermic, because we lost some to the what? To the environment. So literally, this one is exothermic. That is very correct and non-debatable. This one is exothermic, isn't it? What else? Now, of course, this one is endothermic. Why? Products are at a higher energy, as you can see. But what makes them like that? That reactants began their thing alone. But during the course of the reaction, heat came from the environment and interrupted. You understand? So this heat that was coming, it was just adding on more and more energy. So by the time products are formed, you are having a higher energy than what you thought or than what you had. So literally here, it is endothermic. It is a structure for endothermic. Then I want to remind people, there is something we said. Those of you who do biology, you are aware that at that point, leave my screen please. You are aware that at that point where the enzyme substrate complex is formed, it's when enzyme activity is at its maximum. So I want to tell you this, that we agreed that before these reactants give you products, they must first attain a certain amount of energy. And when they reach that energy, they can give you products. What did I say? That these reactants, before they react, they must first attain a certain what? Amount of energy. And when they attain it, they are activated and they can now form what? Products. You understand? So at this point, this circle, that's when the amount of energy, the minimum has been attained. We have now our reactants being activated and they can now give us what? Products. They can now give us what? Products. You get the point? And where you're seeing the circle is where we said, or that's where we said that the activated complex is actually present. So we expect the word activated complex there on the top. Please leave my screen. Who is that? So there on top is where we expect the word activated what? Complex. That's why I expect the word activated what? These energy profile diagrams have a lot of marks. And you all know it can be called the what? The transition state complex, and you know the reasons. Now, there is the other thing I taught. I told you that when the reactants had 20, you look here, that when the reactants had 20, purple color, when the reactants had 20 and lost 15, and the product remained with 5, what was lost is what they call the heat change or the enthalpy change of the reaction. And I'll come here. But the difference, I want you to look here. Let me use, what can I use? Let me use this green. That this is the level, or this is the energy of the reactants. That's what they had. And this is what the products had. Isn't it? That's what the products had. So this difference between what the reactants had and products had is what they call the change. Enthalpy change of the reaction. The reaction is between two things, reactants and products. So the energy change between the two is the energy change. Same thing. Reactants, you very well know that is their energy level. Products, this is their energy level. So this, the energy difference between the two is what they call the what? The enthalpy change of the reaction. You understand? Please, that person dropping emojis in our screen, you remove them, you be organized. Okay, so that is also very important. Now, there is something else I want to teach you. Something very important. And that is something of activation energy. You understand? Remember, we said the reactants are beginning at this level. So from that level up to there, if you can see very well, from that level up to there, the activated complex. Are you seeing that region? Are you seeing that it is between the reactants and when the activated complex was formed? So reactants were moving towards products. We can also have something else. What is that something else? What is that something else? We may have these products trying to go back to the reactants, what we call the backward reaction. If products are going back to reactants, they are also supposed to go through the activated complex. So we also have that level of the activated complex and this level of the product. So we may also have that energy. So that's what they called activation energy. In that, reactants first want to be active before they can give us products. Even the other side, products want to first become active before they can go back to reactants. That's what happens in chemistry. You don't just go to what you want. No, you're supposed to go through the activated complex after obtaining what they call activation energy to make you active. So, activation energy, we shall represent it with letter E, even this one with letter E. In textbooks, they use letter A for the forward reaction and letter B for the backward reaction. Or you can use capital E and F, provided you define that F means forward and B means backward. Infinix, leave our screen. So, you people, this thing is very hard. But trust me, when you understand these simple things, later on, things become very okay. So, to save time, I'm not going to draw the energy level diagrams for each. For me, I'm going to keep with these funny ones. Then I'm going to show you a sample of the energy level diagrams. Then maybe people can comment. Maybe people can comment. Maybe. Okay. I think we are even going to use the energy level diagrams. Okay, let me see here. So you people first tell me whether whatever you're seeing on the screen is okay. Especially those things, energy level diagram, activation energy, activated complex, potential, what, those things. I want someone to first give me, you confirm to me. Are they okay? What is difficult there? Hey, you people, you are not easy. Let me show you some formats here. You see, someone is saying, Doctor, repeat activation energy for forward and backward. People, you get what forward alone means and what backward alone means, then activation alone. You have not been following. Activation energy is the minimum amount of energy you need to just get activated as an activated complex before you go to where you're supposed to go. When I say backward reaction, I want you to look at these. Maybe you will understand these ones. I want you to look here. Here, hydrogen was reacting with iodine to give you hydrogen iodide. This one is what they call the forward reaction. So this was the level for the reactants. So these were reactants. The reactants had to first attain a given amount of energy for them to form the activated complex. And that energy they had to attain is this one, as you can see, EA, activation energy for the forward. That's what they call the forward reaction. You understand? I've explained all this. Let me remove that. Hope you are following. So just have one chance. Now, when I want this one to go back to the reactants, now that's what they call the backward reaction. But before it also goes back, it must go through the activated complex. Remember, for the products to go back to reactants, it's like they are also reacting to go back. So before they react, they need that activation energy so that they are activated and they can go to where they are supposed to go. So this one is still activation energy, but for this case, the backward reaction. Let me tell you, activation energy for the backward reaction is not part of your syllabus. But since it is somewhere on the energy profile, I will have to talk about it. And it is clear because I gave it my time. I believe the activated complex is okay and no issues there. Now, this potential energy, you all know it's supposed to be in kilojoules per mole. You all know how this activated complex is coming about. You all know where the reactants are and where the products are. This difference in energy levels is what they call the enthalpy change. This one has a theta as a superscript, so for them they considered standard. Hope you know that. Now, you people, if I may ask, is there really any problem with this? Not even the labeling, I know it is fine. You people, any problem with that? Any problem with that? Now here you realize reactants had a higher energy and products had a lower energy. So during the reaction, energy was lost, and that is exothermic, and it is represented with a negative. That's why here you're having a negative, and let me hope you people have taken the screenshot to follow it up later. And that is exothermic. People, I don't want you to cry. Yet I gave all parts time, so I don't expect you to be disturbed. I'm still seeing some no's, some no's. You people, I stopped you from saying no and yes. You be like these people, continue, clear now. Even when I have forgotten what I really asked, I can really tell that the point is clear and people are telling me to continue. But when you say no, no, what does no mean? Okay, this is now endothermic. Endothermic, the environment keeps giving the reactants heat. That's why the reactants are down, but the products are somewhere on top. This is the energy level of reactants, this is the energy level of products. The difference in those energy levels is what they call enthalpy change. Because of endothermic, it is positive, as you can see. You see that? Hey, you all know this is the forward reaction. And these are the reactants at this level. This is the energy they need to become activated. So this is activation energy for this forward reaction. If we are considering them in the backward direction in purple, backward like this, that's what they call the backward reaction. The products are at this level. Let me rub off. Hey, you people, you are not easy. So, the products are at this level. Before they go back into reactants, they must also pass through activated complex. It is tit for tat. So they also need some activation energy, but strictly for the backward what? Reaction. And then the rest of the things are obvious. Here they are just putting, instead of reactants, they are putting the exact reactants. Instead of products, they are putting the actual product. Yes. And you all know, on the y-axis, we should have potential what? Potential energy in its very unit. Just like here in our workbook. You can see the potential energy in its unit. So this x-axis is empty, but the word you're supposed to put there is reaction pathway. So x-axis, you put here reaction what? Pathway. Or you can choose to put reaction profile. There are people who prefer reaction coordinate. Let me see what people have here. This one is reaction coordinate. So reaction coordinate is also okay. So people, you take that screenshot for ekizo and endo. Ekizo and endo. So this is endo. Exo and everything well labeled. So people, energy level diagrams, okay? You tell me, energy level diagrams, energy level diagrams. Hope the screenshot is done. Energy level diagrams, tell me in the chat. Energy level diagrams. Energy level diagrams. Let me see if we can find somewhere the definition of activation energy. You look here. Okay, you're also going to take a screenshot for this. I think the next thing here will be questions which we have. Okay. Now here about activation energy. This is very important. This is very important. Let's go through it together. Let me first see what people have commented. Energy level diagrams are okay, very okay, very okay, yeah, okay. So the one saying no, you inbox one of these people, Dr. Trisha, you tell them, inbox them on WhatsApp and they help you. You take the screenshot, send it to Dr. Trisha, she records and she explains. So you're going to tell me whether these statements are okay. I'm going to just read them without explaining. Then you say they are making sense. So the message I expect in the chat is going to be they are making sense. They are making sense. These three. This one I'm going to talk about it next, but separately. So let's read these first three. They are saying activation energy is the minimum amount of energy or minimum energy which is required to be possessed by reactants in order to react and form products. Activated complex is the intermediate unstable compound formed immediately once the reactants have been absorbed the activation energy available. This unstable compound, the activated complex, undergoes bond reorganization by releasing some of the energy to form the final stable product. The activated complex can also be called a transition state complex. You see how reading together is. Do you see how good reading together is after we have explained? Which statement there is not okay? These things of what I forgot, I admit I forgot to tell you that is unstable. But it is clear. The mere fact that it is not our product, but we pass via it. It is an intermediate because we pass via it. And the mere fact that we don't stop there, that means it is unstable. And it is the product which is final that is actually stable. The intermediate is not stable because we just pass via it. These things of bond reorganization, this is just English. It has absorbed the energy. So to form the product, it releases some of it. Don't you see that after the activated complex, the curve goes down? That means this energy we absorb, we release it, or we release some of it to form the product. And the other name is transition state complex. Are the statements making sense? I saw the bond reorganization coming. Bond reorganization is like the activated complex find ways of giving you the final stable product. That's why they call bond reorganization. That the bonds interact, they have a meeting and be like, how can we organize ourselves to get the stable product finally? And that is it. So remember, you look at this. They are talking of the enthalpy of the reaction or the enthalpy change. They are saying it is the difference between activation energy of forward reaction minus activation energy for backward reaction. I want you people to look at that. This is what they are saying. That both of these ones, if you want to get enthalpy, you get activation energy for forward minus activation for backward. Look at our sketches and tell me if it is right. For me, I don't know. I'm also going to first check. You check and see. Remember, somewhere here, it's where we have that activation energy for the backward reaction. Then for this first one, somewhere here, is where we have the activation energy for the backward. So someone is saying when you get that of the forward minus that of the backward, you get the enthalpy change. Is it right? Is it right? Just mere looking at the sketches, is it right that to get enthalpy change, EA minus EB, EA minus EB, whether negative, remember it can be negative or positive. So are things really coming out? Are things really coming out? You see, it is right because you're looking at the sketch. But without the sketch, that means you'll be in an exam. How will you tell that it is right? That means you have to draw. Someone says, Doctor, even during endothermic reaction, we say there is absorption of energy. Does the activated complex still lose energy? We said the activated complex losing energy, it is based on the fact that every time you get the activated complex, the curve goes down. That's what they mean. Immediately after the activated complex, the curve just goes down. That's what they mean by losing energy. The thing of endothermic and exothermic is about the difference in energy level of the reactants and products. Period. Bannai. Echo chiwedde. Echo chiwedde. You people, you know me, I don't teach applications. You learn that from me. Because applications are applications of content. So when you assure me that applications are okay with you, so this is your research work. Imagine research work with notes. You people, me, I don't teach applications. Me, I teach you the concept. Period. So that those are the applications. You can take that screenshot if you really want. Then these are applications of endothermic. So you make research. I don't know, but the good thing, after all, we don't even have project work there. But applications is your research. And nothing concerning applications is supposed to be skipped in your curriculum. It's literally supposed to be taught. You like it or not. It's supposed to be taught. It's almost 6. We started at 3. I wanted this session to be 3 hours. So we have 12 minutes. Let's hurry. Factors affecting enthalpy of a reaction. You've been doing this. These things happened in O-level practicals. So that one you just take a screenshot. They are easy. Temperature, pressure, quantity, physical state. You know what allotropes are. Just take a screenshot and read later. Okay. Now, I'm going to talk about calorimetry. This one is not part of the syllabus, but it has an importance. Not part of syllabus, but it may be of importance in one way or the other. But don't worry, it's not too long. You see, it just ends there. Then here we shall begin types of enthalpy changes. Yes, types of enthalpy changes. So let me explain calorimetry. Calorimetry. Yeah, that one. Let me just talk about it. I have a certain item on thermochemistry. I'm going to check it. If you people can literally do it with what I will have just said, then I think I will end the lesson here, because the other things I want to talk about, and we are going to discuss, because the next things coming are serious, and I think thermochemistry, I'll have 4 lessons, 4 lessons of the remaining lessons of 2 hours. Anyway, be reminded that this holiday we may be forced to study on Sunday. Maybe we get some 2 hours or 1 hour. like the way we covered variance in discrete probability. Can get some time and be like, let's log on for 2 hours, we cover something. But you have a lot of work on the drive, and you're supposed to handle that work on your own. I showed you that work yesterday. Work is already waiting for you people. Work is already waiting for you people. Hey, I don't know. Let me teach you this and I go. Let me comment about calorie. It's not in the syllabus, but it will help us in the future. Eh? They are saying calorimetry is a technique used to measure amounts of heat transferred to and from a substance. Eh? So that heat energy we have been talking of, heat evolved, heat what? There is a technique they use to measure those amounts of heat transfer, and that technique is the calorimetry. And the container used is a calorimeter. How is it designed? It is insulated against heat loss, and they measure the amount of heat involved in a chemical or physical process. So the common calorimeters used in the laboratory, you see, in your practical, why I'm teaching calorimetry, it's not in the syllabus, but you may need to apply it in one of your practicals. So I want to put a note here, because someone may say, why are you really teaching this? You people, do you remember that in O-level you were doing these experiments? Enthalpy of neutralization, okay, those things of enthalpy and heat, things to do with the thermometer and the calorimeter. Do you remember that these things were there in O-level? Or they lied to me? Eh? Because as I was coming for this lesson, I talked to one of the senior people in O-level. He told me that in O-level you were doing things to do with the thermometer as practicals of O-level. Is that right? Or they lied to me? Teacher, when should we present the research work? Research work is always presented via the weekend. People, is it true that in O-level used to deal with the thermometer at one point? Hey, if it's right, then that is nice. So this technique of caliro, not calorie. You know that is a slip of the tongue for us, the Rwandese. Calorimetry. So it is a practical concept. Eh? So I thought it wise to just comment about it. Eh? You people, before you go to the research work I always give you, make sure you've understood what I've given you. Because chances are high that even the research work will not appear anywhere in UNEB. I just want to always you make research and be aware of the content, yeah? So that when you find it somewhere, you're not so shocked. But I don't want you to cram the research work, never. Whatever you need for an exam, I always teach. Research work is full of good to knows. Yeah? I remember sometime last time in the orientation, I told you the difference between the must knows versus the good to know. So this good to know, it's just good to know. You want to become a very competent person in the future. I always hide it in research so that you grow up competent. Then the must knows, these are for our people who just want to pass papers. And that's what I teach. Because all of us want to pass papers, but not all of us want to be competent in the future. Yeah. So the common calorimeters they use, we have the coffee cup and the bomb calorimeters. Yes, they are saying that of the coffee cup, when is it used? Heats of neutralization, solution, and precipitation. Are you saying why I had to talk about this? Because somewhere in your syllabus book, these words are there. Are you seeing the word? The word neutralization is here. The word combustion is here. The word solution is here in subtopic 3. It is here. So if you're going to talk of enthalpy of solution, as a tutor, Why don't I tell you that if you need heat of solution, you're supposed to use a calorimeter, which is a coffee cup. How is it constructed? They use a polystyrene cup with a lid. So make research and find out what is polystyrene. You find out that polystyrene is polyphenyl ethene. I told you alkenes. Polystyrene cannot be an issue. I gave you the other thing of making research about polymerization. You like it or not, you'll come across polystyrene. And they are saying that a thermometer, that's why I've been asking you about use of a thermometer in your level of practicals. This one is usually inserted to measure the heat changes. And you know that you have ever used it. Then the bomb calorimeter, that is for combustion. And strictly combustion of what? Solid substances. You see? Very easy things. Heat capacity, physics students. These are your things. And they are telling you that heat capacity of a calorimeter is determined experimentally. Before I talk about experiments, let me first define for you heat capacity. Just like you hear heat capacity, capacity is quantity. You understand? And remember, a calorimeter is used in these experiments such that in case some heat is given off, it absorbs it. You understand? It is used in experiments. That's why even its heat capacity is what? Determined experimentally. So heat capacity is the quantity of course, heat. But heat strictly absorbed. Why? A calorimeter is a box, and the reaction occurs inside that box. So in case this reaction gives off any heat, the calorimeter absorbs it. But it absorbs it for each 1 degree Celsius rise in temperature. That's why the unit is like this. That heat is measured in joules, but it is heat absorbed per 1 degree Celsius rise in temperature. People, it's not hard. See, there is when I explain something and I feel like it is not okay. But I've said we are using a calorimeter. Inside here, that's where the reaction is what? Is taking place. So if this reaction releases some heat, this calorimeter absorbs the heat. You understand? That calorimeter absorbs the heat. And we are saying, to make it so special among others, it only does this for each 1 degree Celsius rise. And you know that degrees Celsius measures temperature. So it is a rise in what? In temperature. So the absorbed heat, this one, that one absorbed is always in joules, as we said. So it is joules, but the joules absorbed, the measure is done for every 1 degree Celsius rise in what? In temperature. You get? Heat capacity of a calorimeter is the what? It's 6, so let's conclude, is the quantity of heat absorbed by a what? Calorimeter. For each that rise in temperature. And the unit is clear. If you need it, we need to determine it experimentally. And the experiment is your research. What have I said about the research? You may not need the research to pass exams, but it will just make you be that person you really want to become. So please help me only handle research if you have mastered whatever is before the research. So that even when the exam reaches and you've not done the research, you can pass the exam. Yeah. But when you see the research as part of the syllabus book, then those are problems. Those are problems, I assure you, real problems. Okay. Now, so people, you tell me about heat capacity. Just say heat capacity is somehow okay. At least when all the words in the definitions you've tried to, the words in the definition, at least when some of them make sense. Have you gotten something? Just something on heat capacity. Something little, yeah, of course. You cannot understand everything because even me, I've explained, but I've not yet understood it well. I've explained, but in me personal, I'm not convinced about the heat capacity, but I've tried my best. So we thank God that the first subtopic is done. The topic is very big. Thermochemistry, and the subtopics are three. The first one is done because they wanted. Meaning of endothermic reactions, we are done. Exothermic reactions, we are done. The word enthalpy, we are done. Enthalpy change, we are done. Standard enthalpy, we are done. Activation energy, we are done. Standard state, we are done. Activated complex, we are done. Drawing energy profiles, we are done. All the energy profile diagrams, we are done. Explaining them, that is labeling them, we are done. We are seeing visual experiments to demonstrate exothermic and endothermic reactions. Here you are supposed to go and use YouTube. Yes. You know, those who attended our lesson with the mass spectrometer, you saw that we went to YouTube and we watched all these videos. So you go to YouTube and put in this very thing. You just put in visual experiment to demonstrate exothermic reactions they bring. You look for that one, visual experiment, you just go to YouTube. After all, you now know what these things are. Now, this thing of role of activation energy in reaction mechanism, that is your assignment. Because you now know what activation energy is, isn't it? Since you know what activation energy is, you go and now give me the role. You write the role and post it on your status and tag me. That's how we hand in assignments. I don't know if people are aware. So assignment is the role of activation energy because we have defined it very well. So you people, if we can have a lesson per subtopic, that is good. And I didn't want to panic with this topic because that's what most people were complaining about. And that lesson of calculations is the hard one. But it will be easy for you if the introduction makes you love the subject. You understand? So, role of activation energy in reaction mechanisms. How do we hand in? You post on WhatsApp status and mention me. But then don't just go to internet. Don't just go to internet. Don't just go to internet. You first make some research. Now let me use this time. Let me see. So when you look at the syllabus book, where is it? Even this one is done. Yeah? You all know I don't always do for you 100%. I do 80, you do 20. Now, should I have done 95? You're going to just do 5. So next time, we shall do types of enthalpy changes because that is also some good work. Yeah, so maybe we shall do this one per. So we have not been in position to do the types today. Just like the Bible says, we plan and God decides. So we planned to do them today, but God has decided that the types of enthalpy changes, it will be next time. So you can see that we are literally nothing, but God is everything. Okay. So to the premium students who are on, those who are going to be with us in the premium classes, starting today night, there is biology. The moment you're done with biology, there are things you're supposed to do. And those things are awaiting you. Hey, I don't want you to say I didn't tell you. Let me show you. Those of you who are going to be part of premium, today night, I don't know if you're seeing my screen. Today night after biology, I don't know what time Dr. Given is going to start. But in case he delays, there is work already for you to watch on the drive. It is under physical chemistry. Where is it? It is in term 3 work. So you go to term 3 work and go to equilibria 1. So the first topic is chemical equilibria, that one. Those are 8 lessons. Please go and watch that work. I want you to watch it before this week ends, so that on Sunday I put a lesson of chemical equilibria. We do scenarios. I don't know if you're getting me. Because these lessons were recorded sometime and we only concentrated on the normal tasks. That means if you don't finish these 8 lessons, this topic is going to take the whole term. You wait next term. So just assume you do it in a week because there are 8 lessons. Can't you do 2 lessons in a day? Hey, okay, I may push it, but I want to revise it so fast because it has some good scenarios. So that's what we are going to be doing. Those of mathematics, you are aware that topics are waiting for you already. Topics are waiting for you already. Those of math, you're supposed to go and watch probability distributions and random variables. Normal is there, it has 3 lessons. Binomial is there, it has a lesson. Vectors are there, they have 5 lessons. Vectors is even paper 1. I'm even going outside the bracket. Normal 3 lessons, binomial 1 lesson, continuous 5. Those are 10 lessons waiting for you. And you people, you are aware that doing more than a lesson in a day from the drive is hard. If you're too focused, you can only do around 2 because you need to relax. You need to do personal administration, their home chores. So I'm really worried that even the work that is present, you may leave without doing that work. With the pure math, things are worse because integration lessons are there, 9 lessons. Vectors are there, 5 lessons waiting for you. I don't know, when are you going to do that? Nah. Let me pray for you because I really want to bring the scenario so that we revise them together. How much is biology? Biology, Dr. Given, someone put the contact of Dr. Given in the what? In the chat. You can talk to him and bargain. Mm. Very good, Michael Blair. Inbox Michael Blair is the coordinate, is one of the coordinators. Yeah, he can help you join you to the groups of Dr. Given. Yes. Then those who need the previous lessons missed, so you can see our coordinators in the chat. They are trying to respond to you. Yeah. So next time we are doing types of enthalpy changes. So I beg, make some research. So these are the things we are going to be doing next time. Things like accessing the drive, you pay and access. Paying is just 50,000. You access the work for the whole holiday and for term 3. So those in day, you will keep accessing the work. Even those at school, we can guide you on how you can access the work in the computer lab, provided you have sound. Yes. So we are going to do things like bond energy, bond dissociation energy, ionization energy, electron affinity, sublimation energy, atomization energy, enthalpy of formation. Yeah, and we shall stop there. So these are the same things we are supposed to do in a topic called periodic table. So I'm going to sit down and see how I can combine both lessons, so that we have a lesson under periodicity 1, we also have a lesson under types of enthalpy changes. Then we shall have another lesson for only calculations, Hess's law. We do a lot of them. Then after we shall have the last lesson, which will be for lattice energy, hydration energy, and enthalpy of solution. But remember, in this very holiday, we are supposed to do colligative properties and ionic equilibria. I don't know, but you people who are going to school, when you go to school, have it in mind, you're going to come back when the syllabus is done. The syllabus getting done, that means, hey, you'll find a lot of work. So better utilize the work on the drive when it is still little and maximize it, so that by the time we release everything and the work is there from A to Z, when you even have a syllabus book you refer to confirm whether everything was talked about by doctor, you are not bad love. Otherwise, things may be a bit hard. Things might be a bit hard for you, and I'm really worried. But just keep pushing. Just keep pushing. Unless someone has a concern, any concern before I go? Okay. So this is our last few lesson. I don't know. The next thing shall be premium lessons. Do you know what I'm going to be doing for the premium lessons? I will be recording the lessons alone. Then I put them on the drive. So you find the lesson on the drive already recorded. Because after all, you already have their work to look through. That's what I may be doing. But we shall see what to do. We shall be liaising in the premium group and plan for the best thing. Yes, it is 50 for the whole holiday. You pay it once and don't pay again. And when you bring 10 people and they pay for you, don't pay. You study for free until senior 6. Hey, you bring your 10 people, they pay for you, study for free. Payment code, you pay on my number. Let me actually sign out. You have a look at my number. So let me sign out. Yes, let me sign out. You see my number. My number is actually here. Actually, those who want to have a look at our website, we have our website where we even keep all this work. You go to the website and create an account. It is chemmathonline.com. And you're supposed to get used to this website, because with time, this is where we shall be doing the payments from. And with the website, it is even better. You can access it from school very well by simply going to Google Chrome and putting in that. So this is my number, but it is a number that is best for WhatsApp calls. So if you can give me WhatsApp calls, the better. WhatsApp calls for better. So get ready for biology in the night. Yes, Dr. Given is going to come through. You may even look at practicals by Dr. Martin. We have been Dr. Paul. All of us at Makerere University. Yeah, that is it. You take that screenshot. I think it's the only one that wasn't taken. Otherwise, I see no issue in the chat. Okay. Thanks, people, for attending, and good luck. See you in the premium classes.